In classical physics, mass is a measure of the inertia of a body. The mass of an object causes it to resist a change in its speed or direction. The greater the mass, the greater the resistance. This is codified as force equals mass times acceleration. In quantum field theory, on the other hand, the energy of a quantum is represented by oscillations in its field. Since both mass and energy are associated with oscillations in the particle field, we can simply combine Einstein's equation for mass energy and Planck's equation for wave energy to calculate the mass of a wave. The faster a particle is oscillating, the harder it is to change its direction or speed. So this fits our common understanding of mass. Paul Dirac identified the oscillation of a particle between its right-handed incarnations and its left-handed incarnations as a mechanism for fermion mass. The faster the oscillations, the more energetic the particle, the more massive it is. It might seem strange, a particle changing its spin on the fly. But if you recall that particles travel as waves, and spin can be viewed as a phase shift in the wave, it's not too hard to visualize. We'll use electrons as an example. A left-handed spinning electron has a spin 1/2 and carries a weak hypercharge. A right-handed spinning electron has a spin of -1/2 and carries no weak hypercharge. So for an electron to switch from left to right, it must emit a quantum of weak charge and lose a full unit of spin. And for it to switch back, it must absorb a quantum of weak charge and gain a full unit of spin. Now here we had a very large problem for particle physics. It was understood that a derivative of the Z boson was a candidate for the electron spin and charge transition. But there was no standard model mechanism for ejecting and absorbing weak hypercharge out of the blue. Where did the charge go? And where did it come from? In 1964, in order to resolve this problem, Francois Englert, Robert Brout, Peter Higgs, and others proposed a new field that permeated all of space, now called the Higgs Field. They proposed that this field contained a condensate of weak charge. A condensate has the property that adding to it or subtracting from it leaves it the same. A particle carrying weak charge could use a weak-charged virtual Z boson to move the charge to this condensate without noticeably changing the field. And it could use the same Z boson mechanism to absorb a weak charge from the condensate without noticeably changing the field. This was called the Higgs mechanism. With the Higgs mechanism, an elementary particle that carries a weak hypercharge can oscillate and therefore has mass. Electrons, neutrinos, and quarks all carry this charge and interact with the Higgs field, so they can oscillate, and therefore they have mass. Photons don't carry weak hypercharge, and therefore they cannot interact with the Higgs field, and therefore they cannot oscillate, and therefore, no matter how much energy they may have, they have no mass. The process is a little different from particle to particle, and physicists use subtler concepts of chirility, gauge symmetry, and symmetry breaking, but this is the basic idea. You'll note that the particles that interact with the Higgs field are not slowed down. The Higgs field is not like molasses. If the Higgs field slowed particles down in any way, objects in motion would no longer remain in motion. This is not what we see in the real world. Here's one more important idea about mass. The reason the masses are different for different particles is that the coupling strength of the interaction with the Higgs field is stronger for some particles than others. Increasing the coupling strength is like increasing the stiffness of the spring in a harmonic oscillator. It has the effect of increasing the oscillator's frequency. And we have already determined that if we increase a particle's oscillation frequency, we increase its mass.